Swayam Prabha. Digital India. Educated India.
Start with the same equations, start with closed systems. Where I have taken delta W is equal to PdV. I told you in some of the newer books this will be delta Q plus delta W, but in that case delta W will be minus PdV, it is a minor change. But I have taken PVT systems, closed systems, we call these PVT systems, which are of greatest interest in chemical engineering. So if you write this down, so you get automatically at constant S and V, du is less than or equal to 0. That means u can only decrease, so the equilibrium criteria is therefore u is equal to minimum. But this constraint is important, at constant S and V the internal energy has to be a minimum. If it reaches a minimum, then you have equilibrium. The reason I did not start off with equilibrium is, notice that there are only two variables in a pure component system that you can hold constant. So if S and V are constant, u is automatically fixed. So this is not a meaningful criterion when it comes to pure substances. When it comes to mixtures, it is a very important criteria. So it is only in multi-component systems that this criterion will be actually used. But formally I will complete this. You can see similarly, if I now subtract, if I rewrite this as dA, A is u minus Ts, so I will have d of u minus Ts is less than or equal to this minus d of Ts. So you will get dA is less than or equal to minus SdT minus PdV, and consequently you get the result that A is equal to minimum at constant T and V, which is obviously a much more useful criteria of equilibrium, because in most of the chemistry experiments you will be working at constant temperature in the laboratory and at constant volume. And for closed systems again similarly H is a minimum. Remember H is u minus PV, so I subtract off d of, I add u plus PV is H, so I add d of PV, which means I will get TdS plus VdP. Therefore H is a minimum at constant S and P, and simply say similarly, and then G is a minimum at constant T and P. So these two are the most important criteria of equilibrium. In fact GB, you get the same result, these are all redundant expressions, because you know u and s are independent, the rest are just combinations of variables, but it is just convenient in calculus to do everything at constant T and P, but also relates directly to industrial processes which are carried out at constant T and P. The whole process does not have to be at constant T and P. As far as I am concerned, the industry is a black box, something goes in at T and P comes out of the same T and P. So if the envelope is completely dark, you know nothing about it, what goes in is at T and P and the other is at the same T and P, then I have a process at constant T and P for which I can calculate when equilibrium is reached. So if the product happens to be, the product streams happen to be in equilibrium according to my criteria, I know I can't do better than that in the process. We will do that in great detail after we do mixtures. To begin with, I will discuss properties of pure substances. We will discuss work calculations from properties. In most systems that do work, mechanical work particularly, you are not dealing with mixtures. Then we will go on to mixtures, go back to work and calculate separation work, and also calculate equilibrium criteria. So we will start off with the properties of pure substances now. So really there are only two sets of conclusions that you draw from thermodynamics. One is about work, the other is about equilibrium. Exactly two sets of conclusions, and I will show you very general forms of equilibrium expressions which you can use in any situation. In fact, after a while you will find if you go to the literature, they will simply write down the equilibrium criteria, write down an expression in terms of partial differential equations, which after about a month or two of familiarity you will also write down. Everything will always be of the same, all the expressions will be of the same form, except there will be a characteristic enthalpy change, there will be a characteristic volume change, which you will be able to guess after a while. Simply a matter of, almost a matter of familiarity, but you can derive these rigorously. So you have du is equal to Tds minus Pdv. You might say this equation is valid for a reversible process, but I am now looking at changes of state from one equilibrium state to the other state. So I do not care what the process is, I only want to know what the changes in u, how the changes in u s, changes in s and changes in v are related. Now I have a choice here, let me write the equations down, all that you need, and sorry, Tds plus Vdp. As I told you, I have a choice of P and T or V and T as variables, and I want to choose the variables. I will look at this equation. So I have ds, I have to write an equation for s, is going to be partial of s with respect to P dP plus partial of s with respect to T dt. It is also equal to partial of s with respect to V dV I can use either of these criteria, either of these equations for ds, then substitute it back here. If you look at the enthalpy, since P is already chosen as a variable, the expression for enthalpy becomes, for change in enthalpy is simply T partial of s with respect to T dt plus then we have to introduce some variables which you are already familiar with. I will just go through it. Let us say recall that dH is equal to delta Q when P is equal to constant. So when you hold one of the variables constant here in a closed system, then you know the original equation is du is equal to delta Q minus delta W. So delta Q becomes equal to dH, and therefore this is no longer independent, this is no longer dependent on the path, it is independent of the path. So I can define rates, I can add heat to a system, measure its temperature change, and I can ask what is delta H by delta T, delta Q by delta T. This we define as Cp at constant P. One of the earliest people who measured a large number of properties very accurately actually got a Nobel Prize, not for measuring properties but for is Kamerlingh Onnes. I do not know if you know the name. Born in 1850s and in early 19, he lived quite, I think 1920 or 30 he died, but the Kamerlingh Onnes laboratory in Europe, in Netherlands, was a place in the 50s and 60s. If an American thermodynamicist or a transport guy who was measuring transport properties had visited Kamerlingh Onnes laboratory, then he was not considered a good scientist, and it's sort of place of pilgrimage. It was the Mecca for property measurements. You have to turn up there. It was called the coldest laboratory on earth or something, because Kamerlingh Onnes himself was given the Nobel Prize for liquefying helium. He got one of the earliest Nobel Prize winners. He worked with Kirchhoff, became a prof very early. We will get back here. So the specific heat is defined this way. Notice this is measurable, and therefore this is measurable. So the important thing about these specific heats is they are measurable. Everything that is measurable has a special value in thermodynamics. And if it appears on the right hand side, do not try to simplify the equations further. Actually, similarly, the others I can write down. Partial of u with respect to t at constant v is called Cv. This is dou q. Normally you won't be able to divide the heat exchange by temperature differential and get a property, because heat itself is dependent on the path. But if you constrain the process suitably, you can get functions of state, changes in functions of state, and therefore you get properties. Another property that is important, and I will not define it here, is called C sub sigma, which is measured along the saturation line. If you have liquid and vapor in equilibrium and you change the temperature by dT, keeping the vapor and liquid in equilibrium, the heat that is added is measurable, and then you get what is called C sigma. It is a very easy measurement, and therefore it is very attractive. It is related to Cp Cv, we will relate it a little later, but right now we will use the Cp Cv as measurable quantities. So let us take this alone right now. Sort of the whole thing is so redundant, I can do it in 150 ways. There is no point doing it in those ways unless you need it. So if this is true, then notice at constant, you have this equation at constant p, you also have dou h by dou t is equal to t dou s by dou t. At constant p this term vanishes, so this is equal to t ds. In first order differentials work like this. When I differentiate the left hand side with respect to t, if there is a differential here, I can simply divide it by t. You can do algebra of first order differentials. Second order you can't do the same thing, but anyway, so this is equal to Cp. So dou s by dou t is simply equal to Cp. So this part, this is Cp by t, dou s by dou t is Cp by t. Then I need dou s by dou p. So you know how these things are done. And I have to go to s with respect to p. I should get dt plus vdp. I have dg, you just have to juggle these around, and if you look at second partial, if g is a continuous function of t and p, the second partial of g with respect to t and p is the same as the second partial of p and t. This is true only if g is a smooth function, means all the derivatives must be defined. The first order derivative must be continuous function, it should be differentiable and so on. These are generally true. Actually some of these relationships break down at the critical point. There is a singularity at the critical point, but the singularity is so close to the critical point, mostly chemical engineers work by interpolation. They will get to 0.1 degree from this side of the critical point, get to 0.1 degree on the other side, and then do everything by empirical interpolation. The answers turn out to be right, but the critical point itself is a very big point of theoretical interest. In fact, I think there is a Physics of Fluids, it is a very prestigious journal, 1963 or something edition. It was called the critical edition. It discussed the whole, it is this thick a volume only discussing the critical point. If some of you are interested, you should read. There is a paper by Fisher which is very famous, all about this singularity. That singularity gives you a lot of information about structure, but it will go off into a lot of physics but if you are interested you should. So if I do this differentiation with respect to P first, I get V, so this is simply V. If I do the second differentiation, I get partial of V with respect to T, and here you get partial of S with respect to P. So these are your 5 famous Maxwell equations. You do not have to write all of them down, you got 8 variables, 3 choice of variables, that is you can differentiate with respect to any 2 in any order. So what you will have, you have to choose this G, T and P, so 3 out of 8 variables, so 8C3 possibilities, and if you want to be very perverse you can do 8P3 because you can turn them upside down and so on, and you will get any number of Maxwell relations, all of which is meaningless. You should only derive those that you need. For example, S with respect to P is not a measurable quantity, but V with respect to T is, therefore this becomes indirectly measurable. My only aim is to get measurable quantities on the right hand side. So I have S with respect to P, I will now replace it by minus of V with respect to T, and notice when I do the differentiation with T, P is constant, so automatically P here is constant. Notice if you got V with respect to T at constant S, that is not necessarily measurable, but this is measurable. Okay, P, V, T are considered measurable, so all their derivatives are considered measurable. So I have 2 equations, one is an equation for S which says ds is equal to Cp by T dt, plus S with respect to P which is the same as V with respect to T dP. I will not bother to write P constant here, it is sort of from the context it is understood, or you can go back and put it down. Then dH is equal to Cp by T, I am sorry Cp dt plus V minus T partial of V with respect to T dP. So these are the 2 equations that I have to integrate. It is I am interested in calculating H, any 2 variables U and S. If P and T are the variables, it is more convenient to calculate H and S. So this is my equation 1, this is my equation 2. I want to integrate these 2 equations. Now I have further choices, simply because of the redundancy. If let us say this is P, it does not matter, P and T. I have to integrate from point 1 to point 2, I have to integrate from P1 T1 to P2 T2. Let us consider some reference point, this will be P0 T0 reference point. I can choose my reference point as I please because I will integrate from P0 T0 to Pt and tabulate it, and you are not supposed to, I can assign any values at P0 T0, but you do not worry about that value because you will always take differences, you never take absolute values in classical thermodynamics. So I start from here, I want to get some point Pt which is of interest. So since civilized integration requires that you do not go through some path like this, you will get the same answer, but if you are perverse you can choose a path like that and then see how to integrate over it, but since we have enough difficulties without being perverse, we will choose straight line paths on this diagram, either this way or this way. And even this, it is better to decide it once and for all how you are going to do the integrations, because they are entirely arbitrary, you must choose one that is based on convenience. So let us call this path A, this is path B. We have to look at what information you need in order to do the integrations. If you look at, let us take a look at the enthalpy equation, the arguments are very similar for entropy anyway. The enthalpy equation requires that you have Cp information at constant P. So if I follow this path, I need Cp at P0 in order to get to this point, intermediate point, because I am doing that integration at constant pressure. At constant pressure, if you look at this term will vanish, I need only Cp. Okay, then after I turn, it is constant temperature, so this term will disappear. I need PVT information here, I will call it equation of state at T. By equation of state I mean measurements of P, V and T and automatically all their derivatives. This means equation of state or PVT. All our equations of state are practically empirical. You can derive them also from molecular theory, but you will have to have an empirical input in terms of what the intermolecular potential is. Given the potential, I can calculate the equation. So this is what I need along this path. Along this path, you need equation of state at T0, and then here I need Cp information. Cp at P. Now this is where my choice of reference state comes in. If I choose my P0 to be low enough, I know all substances behave ideally. So if I choose this to be low enough, what I need as Cp at P0 is actually Cp for an ideal gas. If P0 is chosen sufficiently low. In particular, I will simply choose P0 equal to 0. Very often you choose P0 equal to 1 because up to 1 atmosphere gases behave ideally, but really varies. Earlier old systems used to use 1 psia, 1 pound per square inch absolute. So it does not really matter, but nowadays the normal charts are prepared with choosing P0 equal to 0 very often, and then T0 can be chosen at as any temperature. As long as you go to sufficiently low pressure, you will get the gas phase and you will get ideal behavior. So the advantage here is that if you go back here, you look at this information, this is 0 for an ideal gas. Right, you know this already. If this is 0, then H is a function only of T, Cp becomes a function only of T. If Cp is a function only of T, we often denote this Cp as Cp0 for an ideal gas. It is not only a function of T, you can actually calculate Cp0 from, you can get it from two sources. One is spectroscopic data. You can measure for low pressure gases, you can measure the specific heat from spectroscopic information, you can get the values. The other thing is you can actually calculate it from molecular theory. So fundamentally you have two sources for Cp0 other than direct experimental measurement of Cp, whereas on this side this Cp is no longer a function of T alone, it depends on the conditions of the gas. So here I need more information than here, and experimental information is the hardest to get. So you simply choose the path where less experimental information is required. So we will always choose path A, simply a matter of convenience. All textbooks that report data, all tables are prepared by doing the integrations along this path, because however complicated a molecule, I can get Cp0 information for that molecule as an ideal gas. So I can always go up to the temperature of interest, then I can do this integration. Of course this temperature will vary, so you really need data at all temperatures, that is a different matter. Here again that is also true of these lines, while you can go on here, you will have to vary this at all pressures, because pressure of interest is not fixed. So what we will do is, so we will settle for integration along A. path A with P reference, often written as P0 as 0. In some books they will say 1, but if the pressure is low enough, if it is 1 atmosphere or 1 psi, anything less than 1 atmosphere, it is completely ideal. But you have to be careful when you use two tables. If one fellow uses one reference point, another fellow uses another reference point, you have to make the conversion. It is trivial, it is simply bookkeeping, so there is no point telling you 1000 times, but if you make mistakes you will get -1 for every number that you copy wrongly from the chart. But anyway, this is what we do. If we do this, let us look at integral of h. So I am doing this calculation h from, or I will write, we will do equation 2 first, integrate equation 2 from T0 P0 to Tp. We agreed we would first do it at P0, so you will get h of T P0. I am integrating from T0 to, first I will do this as T P0, then from T P0 to Tp, 2 steps. So if I am integrating this equation at constant P0, P equal to P0, this term will vanish. I am doing this integration. This is simply integral Cp0 dt from T0 to T. No, sorry, I am doing it at constant P0, correct. Cp0 is not a constant, it is a function of temperature, but that is known, it is assumed to be known. If you want, I will write Cp0 of T dt. Then I have h of T comma P minus h of T comma P0. Now I am integrating from P0 to P of this term. So what I will do here is replace P0 by 0, because P0 is chosen sufficiently low so that the gas is ideal. So V minus T dou V by dou T is 0 from 0 to P0. So the integrand is 0 below that, so I will simply replace this by 0. And then I am going to choose this to be 0, choose or set to 0. That is why you have to be careful when you go from table to table. In one table T0 P0 may be different from T0 P0 from another table. So if that number is different, then you have to add that number on when you want to calculate the, if you want to compare data from two tables. Luckily by now people have accepted many results of this kind. Usually, for example, T0 is as far as possible chosen as the triple point of the substance. Pure substance has a triple point which is invariant. So usually you will choose that as the data. So these are, there are some conventions, but they are not always followed because the correction is trivial. You just have to check the tables. So finally you get one result. The integral of this can be now written like this simply. H is equal to, because it is simply integral 0 to T Cp0 of T dt plus integral, this is from T0 to T, 0 to P of V minus T dou V by dou T so you will find any table or chart on top, it will say H the T0 P0 values will be given at 0 comma 80 degrees K is equal to 0. So right on top of the table, that one line will tell you what T0 P0 is. It will write, they will write their H at 80 comma 0 is equal to 0. Those numbers represent T0 P0. In the chart also they will tell you exactly that H is equal to 0 at this condition, that is your reference condition. Now this is a little trickier to integrate. I will tell you that the trivial thing in this is simply that V with respect to T at low pressure will go as R by P. You will have to integrate from P is equal to 0 to P is equal to P. R by P dP will give you a log P. Log P goes to 0 as goes to minus infinity as P goes to 0. So there is one minus infinity there, so you have to work around it. And the way you work around it is simply in thermodynamics you simply add R by P and minus subtract R by P. So you will get Cp by T dt minus dou V by dou T minus R by P dP minus R by P dP. Now we do the same thing as we did there, you will get the following result. S is equal to, when you integrate Cp by T you simply get Cp0 by T dt from T0 to T, and when you integrate this you will still get the same result, minus P0 to P, actually P0 will be made 0 now, dou V by dou T minus R by P dP then you get this here which is minus R log P plus R log P0 plus S at T0 plus 0. So you are integrating from T0 P0, so you will get this is S at T and P. So S at T and P is equal to, start from S at T0 P0, at P0 you integrate from T0 to T, you will simply get Cp by T dt. The remaining you have to integrate from P0 to P. As far as integrating this is concerned, I replace P0 by 0, because 0 to P0 the gas is ideal, dou V by dou T minus R by P is 0. So that part of the integral is 0, so I have simply added a 0 here. Then I integrate this, I get R log P minus R log P0, right. Now I know there is a problem here because I am going to set P0 equal to 0, but notice that this quantity in parenthesis refers to the entropy contribution at the reference condition. That entire thing is at the reference condition. So instead of setting S at T0 P0 to 0, I will set this to 0, and it does not matter because I calculate S difference between in entropy between 2 points. I will subtract off R ln P0, that same identical quantity from itself, so it will cancel. If I take the limit of P0 going to 0, it will go to minus infinity, so I avoid taking that limit and simply set this component equal to 0. Is this clear? So on top of every chart there will be a chart that gives you thermodynamic properties or tables. It will say H at 0 at 80 0 equal to 0, S at 80 0 plus R log P0 equal to 0. So they will not write S set is equal to 0, and it does not matter because it is the same minus infinity that you are subtracting. You have to be careful, there are different kinds of infinities, so you cannot cancel infinities unless they are identical infinities. In fact, according to George Gamow there are only 3 types of infinities. In fact, he says we have not progressed much as far as infinities are concerned. We are the same condition that the Hottentots were, they could count apparently only up to 3. He says we can also count only 3 infinities, we do not know how to account for more infinities. So that is it, this is the basis of all charts. You have to be careful, if the P0 value that you take is different in two charts, then the different, that R log P difference you have to account for. If it is 0 everywhere is no problem, but if there is a number there and the units are different, then you have to be careful about your choice of P0. Normally the convention is to choose P in bars, take P0 equal to 1, in which case this will become 1, but 1 to 0 to 1 is 0 anyway, so this can still remain 0 to P, it does not make any difference. But this number you have to be careful about when you are comparing two different charts. If it is the same chart, you can blindly subtract. 99% of the time you lose the same chart, same table. So all this, all that I am saying is of no consequence, but if you are taking data from two different tables, please be careful. So these are the two integrated equations, H of T and P is this. So this is the basis of all your, if you like I will write here plus H of T0 P0 and set it and say this is 0. So let us look at the chart of a substance. Normally the charts that are used, you are used to PVT of course diagrams, but the more useful thing is the pressure enthalpy diagram or the temperature entropy diagram. The TS diagram is used very extensively by mechanical engineers. The pH diagram is in many ways more useful for chemical engineering practice. If you look at low pressures, you are talking of really the ideal gas. You are putting the enthalpy, usually it is a choice, the choice is between one intensive variable and one extensive variable, because what you would like to do is to show how the phases differ in properties. So if you have a liquid phase and a gas phase, one of the properties will change, the pressure will remain the same for both, but the enthalpy will be different, and you can read the latent heat by simply taking the enthalpy difference between the liquid and the vapor. Now these are prepared experimentally. What I will do is draw the curves as they appear normally for most substances. You get a liquid plus vapor region, I will trace these regions in a minute. What you do is trace isotherms, isotherms go like this. This is a typical, oh I have not drawn the wrong place. This is temperature T1 less than the critical temperature. There is a critical temperature of course. This is T is equal to Tc, and then above the critical temperature you have complete vapor phase. These are normal qualitative diagrams. The 1 bar line may be somewhere here, usually indicated, this is 1 atmosphere or 1 bar. I think now most of the charts come with the bar. Looking at this, you can say what the lines look like on this diagram. On this diagram they also have plots of constant S and constant V. I have forgotten which is steeper, we will find out in a minute. You can give qualitative arguments and find out which of them is. You may switch that V and S, you just run qualitative curves. For example, if I am looking at H and P, you have, I will go back to this differential equations itself, H is equal to Cp dt you are looking at pH lines, so I am always looking for dou P by dou H to find out what the slope of the line is like. It is easier to get dou H by dou P. I will do all this for per unit mass. So you will find in the charts they use small h in order to indicate specific enthalpy. So if I do this, I get partial of H with respect to P at constant T would be simply V minus T dou V by dou T. So if you look at the isotherms, at very high pressure they will have low value, but the interesting thing is at low pressure dou H by dou P is 0 or dou P by dou H is infinity. You are looking at the inverse of the slope here. So these lines have to be vertical when they come to sufficiently low pressure here. All these lines are vertical. Isotherms are vertical here at low pressure. You are essentially saying they are ideal gases and therefore the enthalpy does not change with pressure, it is function only of temperature. Now let us look at the isentropic and constant volume lines. What I am interested in is dou H, we will make this H, this is small Cp, V dou V by dou T. I am just writing small Cp is specific per unit mass and small v is per unit volume. I want dou H by dou P at constant S. For that it is actually easier to go here to the earlier one. You get is equal to Tds plus V dP. So the constant H with respect to P at constant S will simply give me V. So the isentropic lines, the constant S lines have a slope equal to 1 by V. In calculating dou H by dou P, the slope on this is dou P by dou H, so it is 1 by the other.